Now let's talk about p-bits. This is where we get into probabilistic computing. A p-bit is just a probabilistic bit. If a p-bit is a probabilistic bit, then the value of the bit changes probabilistically. And if it changes probabilistically, we can't keep track of the bit's precise value. We can only keep track of a statistical distribution of the bit's value. We can represent the p-bit with a vector that's a linear combination of bit vectors. In this case, we have a p-bit where the first element is alpha and the second's beta, and we form it by taking the bit vector for a bit in the configuration 0 plus beta times the bit vector for the bit in the configuration 1. Each of these coefficients, alpha and beta, correspond to the probability of the p-bit having a particular value. And as these coefficients are probabilities, they must sum to 1. Alpha represents the probability of the bit having a value of 0, and beta is the probability of the bit having a value of 1. Now this slide is basically a copy of the slide for the bit vectors, because you can do all the same things here with a p-bit vector. You can combine p-bit vectors for singular p-bits into a single big p-bit vector by combining them with the Kronecker product. And when you do it, each element of the p-bit vector then represents the probability associated with that particular configuration. If you look at the bottom, we combine the p-bit vector for p-bit A with the p-bit vector for p-bit B to get a combined p-bit vector AB. And then if we expand out the p-bit vector AB, you can see that alpha is the probability of the system being in configuration 0, 0. Beta is the probability of the system being in configuration 0, 1. Gamma is the probability of the system being in configuration 1, 0. And delta is the probability of the system being in configuration 1, 1. Recall that the dynamics of a system is time reversible, and this can be described by one-to-one maps, these being permutation matrices. For a probabilistic computer, each logic gate, therefore, can only be described by a linear combination of permutation matrices, each weighted by their probability of occurring. If you look at the bottom there, we're defining a doubly stochastic matrix, which is usually represented with an uppercase gamma, as equal to a 25% chance of the swap permutation occurring, plus a 75% chance of the C0 permutation occurring. The reason they're called doubly stochastic matrices is because if you look at this matrix, you can see that each column sums to 1 and each row sums to 1. A doubly stochastic matrix is just a probability distribution of permutation matrices, where you don't know for certain which permutation will be applied, but you can assign them all a probability. You can also create a discrete p-bit evolution law, which looks just like the one for the bit vector. If we're evolving the p-bit vector, we just need to multiply the logic gate represented as a doubly stochastic matrix by the p-bit vector, and it gives us a new p-bit vector, which is the evolved form. And in the same way, you can combine all the operators together and then multiply it by the bit vector all at once. You can do the same thing with the p-bit vector as well. So now let's talk about Bayes' theorem. Consider we have a p-bit vector where the probability distribution of a 2-bit computer, so it has 2 bits of memory, is 10% for the bits being in configuration 0, 0, 20% for the bits being in configuration 0, 1, 30% for the bits being in configuration 1, 0, and 40% for the bits being in configuration 1, 1. Now consider that we read the computer's memory state and find that the most significant bit has a value of 1. So keep in mind we didn't read the least significant bit's value, we only read the most significant bit's value. If we know the most significant bit's value, we don't need to represent it probabilistically anymore because we know its value. So we can update the probability distribution to reflect this new knowledge we have. We do this using Bayes' theorem. So you can see Bayes' theorem below. It says the probability of a hypothesis given some evidence equals the probability of that evidence given the hypothesis times the probability of the hypothesis. And you do all of that divided by the probability of the evidence. So what do these conditionals mean in Bayes' theorem? So the hypothesis is that the computer's memory is in a particular bit configuration, and the evidence is the bit of information that we actually observe. The probability of a hypothesis is just the associated element in the p-bit vector. In the example p-bit vector, the probability of the hypothesis that the computer's memory state is in the configuration 1, 0 is 30%. The probability of the evidence given a particular hypothesis is either 100% if the hypothesis is compatible with the evidence, or 0% if the hypothesis is incompatible with the evidence. For example, the probability of the evidence that the most significant bit is 1 is 0% given the hypothesis that the computer's memory state is 0, 0, as well as the hypothesis that the computer's memory state is 0, 1. However, it is 100% given the hypothesis that the computer's memory state is 1, 0 or 1, 1. The probability of the evidence is the summation of the products of the probabilities of the evidence given a particular hypothesis and the probability of that hypothesis. So now let's actually go through some of the math of a applying Bayes' theorem in the case where we measured the most significant qubit to have a value of 1 for this p-bit vector. As you can see in the second line, these are the probabilities of the evidence given one of the 4 possible hypotheses for the current configuration of the bits in the computer's memory. And in the third line, we compute the probability of the evidence, and then that gives us enough information to compute the probability of the hypothesis given the evidence, which is just Bayes' theorem. And when you compute Bayes' theorem, you can see we update our probability vector to 0, 0, 0.4286, and 0.5714. Now, let me give you a simpler way to think about Bayes' theorem without having to actually go through this whole complicated calculation. So even though the mathematics sound complicated, if you actually look what's happening, it's very simple. All we're doing is we're zeroing out the probabilities of the vector that aren't compatible with what we observed. So if we observe the most significant bit with the value of 1, then we know it's impossible that the system's in the configuration 0, 0 or 0, 1, because in both those configurations, the most significant bit's value is 0 and not 1. So we just set those probabilities in the vector to 0, and then we just renormalize the vector. And we renormalize it by taking its sum, which in this case is 0.7, after we've zeroed out those values, and we divide it by its sum. And this updates our probabilities, so now we're saying that there's a roughly 43% chance the system is in the configuration 1, 0, and a roughly 57% chance the system's in a configuration 1, 1. So that's really all Bayes' theorem is. You just zero out the things that aren't compatible with what you observed, and then you renormalize the p-bit vector by dividing it by its own sum. You might wonder why we're even using this weird configuration space representation to begin with. Why don't we just represent the bits individually? If you're just evolving deterministically the values of bits, you can do that. But you can't do that if you're evolving the bits probabilistically. This is because if you describe the probabilities of the bits individually, you lose information regarding correlations. So if you look at the bottom, there are 3 p-bit vectors. One describes a case where the bit values are entirely uncorrelated. The second p-bit vector describes a case where the bit values are perfectly correlated, so that the values are guaranteed to be the same for the 2 bit. And then the third one describes a case where the bit values are perfectly anti-correlated, meaning that they're guaranteed to have opposite values. However, if we think about the probabilities of each bit taken separately, so we consider just the probabilities of one bit and not both of them together, then it's pretty apparent that the probabilities of just one bit on its own is going to be 50% 0 and 50% 1. But that's true for all 3 of these cases. In all 3 of these cases, the probabilities of the bits individually is 50% for 0 and 50% for 1. So if you just describe them individually as 2 separate p-bit vectors, they would both just have 0.5, 0.5 as their 2 elements. And so if you describe them separately like this, then you lose the information regarding the possible correlations they might have between each other. So when there are correlations between the bits, we say that the p-bit vector is non-factorizable because you can't break it out into separate p-bit vectors without losing information on those correlations. In the perfectly uncorrelated case, you can actually factorize it out, because if you have 2 p-bit vectors where the elements are both 0.5, and then you take those p-bit vectors and combine them back together by doing the Kronecker product, then you find that you get this uncorrelated vector. But you can't actually produce the correlated or anti-correlated vector from the Kronecker product of any 2 individual p-bit vectors. So it's a necessity when you're describing a probabilistic system to use this representation in configuration space. You can't represent the p-bit vectors individually. Even though factorizing the p-bit vector into smaller separate p-bit vectors can lose information and lead to wrong predictions, we can choose to do it anyways if we want, if we're just curious the statistics on bits considered in isolation from the rest of the system. So for example, if we have a system of 3 qubits and we're only ever going to measure one of them, we can still separate them out just to see what is the probability of just that one bit on its own. And this process is known as marginalization. To do this, all we have to do is multiply our p-bit vector by a matrix as shown below. The matrix is formed from the products of OJ, where J is the position of the bit and N is the number of bits in the system. So for each element OJ, we choose the identity matrix if we want to not marginalize over the bit in position J, meaning that bit is removed from the vector. And we choose this row vector 1, 1 if we want to marginalize over the bit in position j. For example, if we have a 2-bit system and we want to marginalize over the least significant bit, meaning we want to remove it from the p-bit vector, then that means we want to marginalize over the bit in position 2. O1 would be the identity matrix, and O2 would be this row vector. And we would only have O1 and O2 in that case, because the system would only have 2 bits. We would combine those together with the Kronecker product, multiply it by the p-bit vector, and then we would get a new p-bit vector, which has removed the least significant bit.